Hello dear students, welcome to my YouTube channel JEE Academy. In this video, I'll be talking about location of roots, which is a topic from quadratic equation, and it has a very good weightage in JEE Mains as well. And frequently the questions have been asked from this topic. So let us understand what it is all about. So here the first case is if both roots of quadratic equation ax squared plus bx plus c equal to 0 are greater than a fixed number k. Okay. So what is the first thing we have to do here is just assume that the equation which is given here becomes a polynomial. So you write it down as ax square plus bx plus c. Okay, that is the first step. Now, since it is a polynomial, so now we can draw the possible graphs of this. So let's see how to draw the graph of this one. So let's draw it for a greater than 0. So I know that either it will be opening upwards, something like this, and this is the x-axis, and here is the number k. Okay, so both of these roots are greater than k. So I can say this is alpha and this point is beta, right? So alpha and beta are greater than the given number, which is basically k. Okay. So similarly, I could have for a greater than 0, something sort of this parabola opening upwards, isn't it? And here is the number k, right? So now these are the two possibilities for a greater than 0. Now let's draw the graph of a less than 0. So what it will be? Opening downwards, isn't it? So here it is k, and this is your alpha, and this point is beta. So here also alpha and beta are greater than the given number k. And then the next graph for a less than this, I could have is just touching the x-axis and going downwards. And similarly, I could have k here, and my alpha beta are the roots which are greater than this. Now, the next thing is to check the property, observe what and all we can, conclude from these four conditions. So these are the four possible graphs which we can make for this given condition that the roots are greater than the fixed number k. All right. So what we see here is every time the vertex, if I talk about the vertex which is minus b by 2, it is always greater than the given number k. Yes or no? Here also if I'll talk about, so this is the vertex minus b by 2. This is greater than k. Here also if I'll talk about minus b by 2, it is greater than k. And here also minus b by 2a, it is greater than k. Okay. So when this scenario is there, when the fixed number, the roots are greater than the fixed number, what we see here is vertex is always greater than the given number. Okay. Next thing. Next thing to observe over here is if I check the value of f of k, right, in this particular case. So it is greater than 0. Similarly, here if I'll check, then also the value of the function at k is greater than 0. And here if I'll see, it is negative, isn't it? F of k is less than 0. And here if I'll see, here also f of k is less than 0. This is the second observation. Third observation is, you see here, the graph is crossing the x-axis. Yes or no? Correct. So the graph is crossing the x-axis. That means, and it is touching also. So here, can I say discriminant will be greater than 0? Here discriminant is equal to 0. Similarly, here discriminant is greater than 0. And here it is equal to 0. Right. So these are the three characteristics which we can see from these four given graphs. Okay. So let's try to conclude this. First one is the vertex. Okay, here, 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 and here. Right. So what is the first condition we got? Minus b by 2a is greater than k. Okay, this is true for all. Then second condition, what we see here is discriminant is either greater than 0 or it is equal to 0, isn't it? And then thirdly, we had seen that f of k is greater than 0 for the first two graphs when a is greater than 0. And f of k is less than 0 for a less than 0 in the second two graphs. So now what we can conclude from here is, first, discriminant should be greater than or equal to 0. Secondly, we have to check the vertex is greater than the given number k. And then third, so basically if I'll combine these two equations, right, this condition and this condition, if I'll combine, so you just check the product of this, a times f of k. This will always be greater than 0 because a is greater than 0 and f of k is also greater than 0. So both are greater than 0, isn't it? In all the cases. And in the second scenario, when a is less than 0 and a is less than 0, here also what we see here is a is negative and f of k is also negative. So the product of a times f of k is again greater than 0, right? So combining these two conditions, what we get is a times f of k is basically greater than 0. So these are the three conditions and you have to cram it as it is. All right. So this is the concept for the first case. Now let's see some questions based on this, then it will be more clear to you. So here we have the first question. So it says, find all possible values of d for which both roots in the equation exceed the number 3. Okay. So what is the first step? I'll write the solution. First step is to assume that the equation is your polynomial as x squared minus 6dx plus 2 minus 2d plus 9d squared. Okay. So here A is 1, B is negative 6d, and C is the constant, which is complete 2 minus 2d plus 9d squared. So this is what we have. Now, this belongs to which category? Exceed the number 3. So now the next thing is to write the number of graphs, right? To draw basically all the possible graphs corresponding to this scenario. So I can have my graph like this, where this is the number 3, and here are my roots, isn't it? Or I could have it like this, where the number is 3, or I could have a graph going downwards where this number is 3, or I could have 3 and the graph is going like this. So these are the 4 possible conditions we have. Okay. So now we will check all these conditions one by one, which we have seen. So the first condition is d should be greater than or equal to 0. Right. So I'll just plug in d is minus b whole square 6d whole square minus 4ac. A and c is 2 minus 2d plus 9d squared is greater than or equal to 0. So if I'll solve this, I'll get 36d squared, right? Minus 8 plus 8d minus 36d squared is greater than or equal to 0. So what we get from here is this cancels out. We get 8d is greater than or equal to 8, or d is greater than or equal to 1. So this is what we get from here. And we have to find the value of d. Now second condition is minus b by 2a should be greater than k, where the value of k is this, right? So this is the value of k, which is equal to 3. So now what I need to do here is, let me use a different color. So b is 60, negative and negative becomes positive, divided by 2a, and this is 3. So 6d is greater than cross multiplication 6. Therefore, d is greater than 1. This is what we get from here. And then the third condition is a times f of k should be greater than 0. So a is 1, and then f of k means here f of 3, right? So f of 3 would be what? It would be 3 squared minus 18d plus 2 minus 2d plus 9d squared is greater than 0. And if I'll solve this, I'll basically get 9d squared minus 20d plus 11 is greater than 0, which can be factorized as 9d minus 11 and d minus 1 is greater than 0, right? So from here, what we get is, put them on the number line. So one root is 1 and the other one is 9 over 11. So using Wavy Curve method, we get plus minus plus, and we need positive answer, so it will lie in this range. Now combining all the three conditions, our final answer here is, let me erase these graphs and conclude the answer here. So final answer, D is greater than or equal to 1 and D is greater than 1 and D is greater than 9 by 11 to infinity and D is less than 1. So our final answer goes from D belongs to 9 by 11 to infinity, right? So this is the common for all of this. I hope it is clear to you. Now let's do one more question based on this. So we have the next question. It says find all the values of A for which both roots of the equation exceed the quantity A. So again, following the same concept, assume that the given equation is your polynomial in f of x as x squared plus x plus a, and then all the possible graphs. So either it will be like this, or it will be touching, or it will be going down, or it will be crossing this. So here we have A, 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 and A. So these are the four conditions. Now solving each condition one by one. So the first thing is discriminant is greater than or equal to 0. So we'll write b square, which is basically 1 minus 4ac is greater than or equal to 0. From here we get a is less than or equal to 1 by 4. Second condition, minus b by 2a should be greater than the number quantity, which is a itself, and b is 1, so negative 1 divided by 2 is greater than a. So we get a less than minus 1 by 2 from here. A is less than or equal to 1/4. And then solving the third condition, which is basically your a times f of a should be greater than 0. Okay. So a is 1, f of a would be, just plug in the value of a here in place of x, so it will become a squared plus a is greater than 0. So what we get from here is a squared plus 2a is greater than 0. And the roots are basically 0 and minus 2. Using the wavy curve method, we have plus, minus, plus. So the possible solutions are here. And therefore, combining for all, the common answer, a is lesser than minus 1 by 2, a is lesser than 1 by 4, and then a is lesser than minus 2, right? So combining all of this, what we get from minus infinity to minus 2, because minus 2 is the smallest of all these three, right? You can put them on the number line. So that's your final answer. I hope the concept is clear to you. Now, let's see one more question based on this. This one is an interesting one. So it says determine the values of a for which both roots of the quadratic equation a square plus a minus 2 x square minus a plus 5x minus 2 equal to 0 exceed negative 1. So the very first step is to assume that the given equation is a polynomial in x plus a minus 2. We have x squared minus a plus 5 times x minus 2. So that's the polynomial. Now, how do we solve it? It is saying exceed negative 1. So again, it is of the same concept. So all the four graphs will be there. Now solving for the first condition, we know that d is greater than or equal to 0. So if I'll just plug in b square, b is minus a plus 5. So negative a plus 5 whole square will be a plus 5 whole square with a positive minus 4ac plus a minus 2, and c is your negative 2. Should be greater than or equal to 0. And therefore solving it further, you get 9a square, and simplifying it, 18a plus 9 is greater than or equal to 0. Or we could say this is a square plus 2a plus 1 is greater than or equal to 0. Therefore, a plus 1 whole square is greater than equal to 0. And this is true, right? Square of any number is always greater than equal to 0. And therefore, what we conclude from here, a belongs to all real numbers because it's a square. Now, solving for the second condition. Second condition is the vertex minus b by 2a should be greater than the given number, which is minus 1. B is negative. So this will become positive. 2 times a squared plus a minus 2 should be greater than negative 1. And then solving it further, we get, take this minus on to left hand side, divided by 2 times a squared plus a minus 2 plus 1 is greater than 0. So if we'll take the LCM here, the LCM would be 2a squared plus a minus 2. So I'm directly solving it here. Okay, so finally what you will get after factorizing it, 2a plus 1 times a plus 1. Right, if you'll take the LCM and then cancel out the common terms, you'll factorize it. Okay, and the denominator is also factorized with a plus 2 and a minus 1 greater than 0. If you'll put them on the number line, so all the possible roots are negative 2, negative 1, negative 1 by 2, and positive 1. So if I use the wavy curve method, plus, minus, plus, minus, plus. So from here, what we get is a belongs to minus infinity to minus 2, union, minus 1 to minus 1 by 2, union 1 to infinity. This is what we get. And then solving for the third condition, which is a times f of minus 1 should be greater than 0. So we have the leading coefficient a squared plus a minus 2 and f of negative 1. It basically gives us negative 1 if I'll plug in. So a squared plus a minus 2 and then plus a plus 5 minus 2. So if you'll solve this f of negative 1, you'll basically get this thing as a squared plus 2a plus 1. It should be greater than 0. Now, a squared plus a minus 2 can be factorized. We have already done that with a plus 2 and a minus 1. And this a squared plus 2a plus 1 is nothing but a plus 1 whole squared greater than 0. So all the roots, if I'll put on the number line, we get here minus 2. And then we get minus 1. And then we have 1. And now using the wavy curve method, here we'll get plus. And then here also, here we'll get negative, negative, and then positive. Okay. So this is what we are going to get. And therefore, a belongs to minus infinity to minus 2, union 1 to infinity. Now we have to check the common answer. So from the first case, we see here that it belongs to all real numbers. So we don't have to worry about it. Now next thing is we see here minus 2 to infinity, negative infinity, this one. And here also we have it. And then 1 to infinity, 1 to infinity. So final answer, we conclude a belongs to minus infinity to minus 2, union 1 to infinity. That's a final answer. So I hope students, you have understood the basics of this case. Now we'll study about the second case, which is when the number of roots, right, they lie between, or you could say the either side of a fixed number. Okay. A quadratic equation lie on either side of a fixed number k. Okay, so we have already seen if that both the roots are greater than the fixed number k. Now the second scenario is if both roots of a quadratic equation lie on either side of a fixed number. So as usual, let's assume that there is a quadratic equation and that becomes a polynomial ax square plus bx plus c. This is the very first step. Then it says it is greater than a fixed number. So here one condition is, what they try to mean is, one of the root is smaller than k and beta is greater than k, right? This is the case here. Now, if I talk about the graphs, all the exhaustive graphs of this scenario would be, let's take a greater than 0. So alpha is smaller than k and beta is greater than k. So the graph could be like this. Okay. So here it's alpha, here this point is beta, and the fixed number here is k. So that is k. Or else I could have a graph for a less than 0. So it would look something sort of this, a parabola opening downwards. So again, we have a fixed number k here, and this is alpha, and this is your beta. Okay. So these are the only two possible cases we have of the graphs, isn't it so? Now, what we see here is, by default, right, discriminant is greater than 0. Yes or no? These are the observations. So whenever we have these kind of scenarios where, the roots lie on the either side of k, then naturally the discriminant will be greater than 0, isn't it? So I don't have to consider this case. So I can write this as by default. Okay. And then the next thing is to talk about the vortex. Vortex is negative b by 2a. So if I'll check the vortex over here, right? So now this vortex could be either equal to k minus b by 2a. It might be equal to k, or the vortex could be less than k, right? It could be here less than k, or it could be more than k. Similarly here, the vortex minus b by 2 could be equal to k, the given number k, or it could be less than k, or it could be greater than k. So that means your vertex has no meaning, isn't it? So this condition is not to be checked. Okay. No need to check, because there is no point of checking it, because of the very reason that the vertex could be equal to k, or it could be less than, or it could be greater than. Right. So this discriminant is greater than 0 by default. So no need to check. Okay. Now, the third condition, which is very, very important, is now the values at k, right? So f of k, when a is greater than 0, then f of k is less than 0. And when a is less than 0, f of k is greater than 0, isn't it? So if I'll take the product of a and f of k, what I get here is a times f of k is less than 0. Positive into negative is negative. And here also, if I'll see a times f of k, that is also less than 0. Right? So this is the only condition which we need to remember. So therefore, what we conclude from here is the condition for the roots to be on either side of a fixed number k is a times f of k is less than 0. This is the only condition we need to check. All right. Perfect. So now let's do some questions based on this. Okay. So here we have the first question, which says, find the value of k for which one root of the equation x square minus k plus 1x plus k square plus k minus 2 minus 8 equal to 0 exceed 2 and the other root is smaller than 2. Okay. So as we know the step 1, let's assume that f of x is equal to x squared minus k plus 1x plus k square plus k minus 8, right? Let this be a quadratic polynomial. And now the only case what we have for this is opening upwards or opening downwards. So we know that in between there is a 2 and the roots alpha and beta are on the either side of it. Okay. So one is lesser than 2, one is greater than 2. All right. So now the condition here what we have is a times f of k should be less than 0. A is 1 and f of k. K value is how much? 2. So f of 2 should be less than 0. Now we need to figure out how much is f of 2. So f of 2, if I just plug in here 2 value, that means 2 square is 4 minus 2k minus 2 plus k squared plus k minus 8 is less than 0. Okay. Now, we're solving this, simplifying it further, we get k squared minus k minus 6 is less than 0. And therefore, the factors are k plus 3 and k plus 2 less than 0. Putting it on the number line, we get minus 3 and minus 2 using the wavy curve, plus minus plus. So what we get from here, sorry, this thing is minus 3, k minus 3 and k plus 2. So this becomes minus 2 and this becomes 3. Okay. So now here using the wavy curve method, what we get, k belongs to lesser than 0, minus 2 to 3. And that's your answer. Okay. Now let's see one more question. Question 2. Find the set of values of a for which zeros of the quadratic polynomial a square plus a plus 1 x squared plus a minus 1 x plus a square are located on either side of 3. So this is also of the same category, case 2. So first step is to assume it to be a quadratic polynomial. So we get a square plus a plus 1, and then we have x squared plus a minus 1x plus a squared. Now the condition for this is what? A times f of k should be less than 0. A here is a square plus a plus 1 times f of 3. So f of 3 would be 9. So 3 square is 9. So if you just plug in x as 3, 3 square is 9. 9a square plus 9a plus 9 plus thus 3 into a is 3a minus 3 plus 9 is less than 0. Okay. So now what we get from here is 9a square plus a square, correct? Plus 9. So this was actually a square, sorry. So 9a square plus a square gives you 10a squared plus 12a plus 6. All right. And here we have a square plus a plus 1 multiplied by this. Now, if you'll see this a square plus a plus 1, this is true for all real values, isn't it? Isn't it? It is always basically positive. So a belongs to all real numbers. Now, we have this thing because this is always positive, right? A square plus a plus 1. Since a square is positive and 1 is also positive, so negative number square plus 1 is always greater than a, the negative number itself, right? So a belongs to all real numbers and this entire quantity is always greater than or equal to 0, isn't it? So now only this will be equal to, I mean lesser than 0. So if I'll take 2 common, I'll get 5a square plus 6a plus 3 to be less than 0. So what I see here from the leading coefficient, how the graph of this will be opening upwards. And if I'll check the discriminant, it is b square 36 minus 2060. Right, so discriminant is basically less than 0. That means the graph is above x-axis. So what we see here is there is no value of a for which it is lesser than 0. So the graph of 5a square plus 6a plus 3 is always above the x-axis and therefore a belongs to 5. Now what is common between a belongs to a real number and a belongs to 5? Nothing is common, so final answer a belongs to 5. That is the final answer over here, right? So this means what? No values of a will satisfy this condition. So final answer, what we conclude is no values of a. Okay, now let's move on to the next case, which is the third case. Third case says if one root of quadratic equation ax square plus bx plus c equal to 0 is less than k1 and the other root is greater than k2, right? Says that the number k1 is lesser than k2. So first step, as usual, assume the given equation to be polynomial in x, bx plus c. Now, if I'll talk about the graphs, all the possible graphs. So for a greater than 0, the first graph will be like this, where we have here k1 and this is k2. So this is our alpha and this is our beta, right? So one is less than k1 and then the other root is greater than k2. Either this is the possible graph, and then we can have for a less than, so opening downwards. So again here k1 and k2 we could have like this, and now here also alpha is less than k1 and beta is greater than this, right? So here also, if I'll observe the sign of the discriminant, right? So clearly here discriminant is always greater than 0, right? So no need to check. By default it is. No need to check this condition, because by default discriminant will be greater than 0. Then only it will cross the x-axis twice. Okay. Now, if I'll talk about the vertex. So what we see here, vertex minus b by 2a. Either it is in between k1 and k2, or the vertex could be equal to k1, or it could be equal to k2, right? Or it could be less than k1 or greater than k2. Yes or no? Similarly, here if I'll talk, the vertex could be between k1, k2, or the vertex could be equal to k2, or it could be equal to k1, or it could be less than k1, or it could be greater than k2, right? So what we conclude from here, vertex which is minus b by 2a, no need to check. Okay. Now the third condition what we need to see here is that for a greater than 0, if I'll see f of k1, right? So f of k1 here you could see it's negative. F of k2 is also negative. So we have f of k1 is negative and the sign of k2 is also negative. And here when a is less than 0, f of k1 is positive and f of k2 that is also positive. So what we conclude from here, k1 is greater than 0, f of k2 is also greater than 0. So if I'll see the product of these two, a times, when a is positive, f of k1 is negative. When a is negative, f of k1 is positive. So either of it have opposite signs. So what we conclude from these two is finally, I could say, a times, the only condition which is true here is, one is positive, one is negative, is less than 0, and a times f of k2 is also less than 0. So this is the only condition which we get from here. Only. Got it. So we don't have to check D, neither we have to check the vertex here. The only condition is this. Now, one might think that f of k1 is positive, f of k2 is negative and positive, isn't it? So the product of, f of k1 into f of k2 should always be greater than positive, right? It should be greater than 0. But that is not actually true. So if you'll see a graph, what I'm trying to say here is f of k1 into f of k2. Since both are positive, so their product is positive, right? So if you'll consider this graph where you have k1 here and k2 here, right? So although f of k1 and f of k2 was positive, but what we see here is the roots, right? They are no longer satisfying the condition of one is smaller than and one is bigger than. So both alpha and beta are actually greater than k1 and k2, right? But here the condition is satisfied. F of k1 times f of k2 is greater than 0, right? So we cannot take that case. So the only case what we get here is a times f of k1 is less than 0 and a times f of k2 is less than 0. All right. So now let's do one question based on this. So the question says, find all values of k for which one root of the quadratic equation k minus 5x squared minus 2kx plus k minus 4 equal to 0 is smaller than 1 and the other root is greater than 2. So how do we proceed here? First step, to assume the given equation to be a polynomial, k minus 5x squared minus 2kx plus k minus 4 equal to 0 is smaller than 1 and the other root is this. So what are the conditions? A times f of k1 is less than 0, all right, and a times f of, so let me just plug in these values here, k1 and k2 values. So what we have here is, this is 1 and this is 2 is less than 0. Now the leading coefficient A is k minus 5, and then f of 1 is nothing but k minus 5 minus 2k plus k minus 4 is less than 0. And from here we get leading coefficient k minus 5, and then f of 2 is 4k minus 20, and then x is 2, so minus 4k plus k minus 4 is less than 0. So if we solve this, we get k minus 5, and then k plus k and 2k cancels out. We get minus 9 is less than 0. So from here we get k minus 5, multiplying both sides by minus. So this will become greater than 0, or k is greater than 5. This is what we get from the first case. And from the second case, we get k minus 5. 4k and 4k cancels out. We get k minus 24 is less than 0. So put them on the number line. We get 5 and 24, and using Wavy Curve Method, plus minus plus. So where it is less belongs to 5 to 24. Isn't it? Now what is common between them? K is greater than 5. Common thing is 5 and 24. Right? So what is our final answer? This itself is our final answer. K belongs to 5 to 24. Common between this and this is this. Okay. So I hope you have understood the third and the second scenario of roots lying between or either sides of the given number.